Thank you for joining my session today on the Rethinking Storage for the AI/ML era, disaggregated storage powered by flexible data placement. I'm Satish Kumar from Samsung Semiconductor India, and I have my co-authors Amit Devkhan, Arun Kumar Singh, and Ratish Gopinath, who also worked along with this paper in this presentation. Here's the agenda for today's discussion. I wanted to talk about some high-level overview of generative AI and wanted to take into the Stable Diffusion, one of the key model which is so popular in the generative AI. And I wanted to talk about a couple of storage aspects with respect to storage AI, Stable Diffusion. And I wanted to highlight some of the on-prem deployment with respect to NVMe-oF fabric. And wanted to highlight a couple of storage challenges what we have seen in the Stable Diffusion, some of the I/O characteristics, and finally wanted to cover up some of the FDP and the right amplification factor with respect to the storage diffusion application. So generative AI. So AI is now everywhere. Since then this LLM got introduced, this AI is taking into the different world. Now with the help of generative AI, we can able to generate most of the images, text, audio, and video in the fraction of seconds, which literally revolutionizing the various industries such as manufacturing, design, gaming, education, medical, or even multiple, including IT. President's research predicted that by 2034, the market value of the generative AI is around $1.005 trillion. Which is a huge business which exists today in the generative AI. This generative AI not only demanding more GPUs, but it's a very storage-hungry applications. With the current prediction from Grand View Research, the storage infrastructure, which includes both hardware and software, it's going to reach somewhere around 25.9 compound growth of by 2030. So this is a good time. The storage is being used in training, checkpointing, inferencing, and the retrieval augmentation generation. So it's a good time. We need to think to build a high performance, highly reliable, and a good petabyte of capacity, and with high secure storage for meeting the generative AI workloads. So let me take into the Stable Diffusion, one of the key model that has been introduced in 2022. This is a deep learning based model. Basically it used for text to image generation. So this was been an open source model released by Stability AI, and since then this has been used widely in design, entertainment, gaming, healthcare, and even predominantly in the fashion technology industries. The Vision research predicted that by 2033, this AI image generation business, it's somewhere around $1.84 billion. Right side you can see an image which was generated from the text prompt, a photograph of an astronaut riding a horse, which is an imaginary image, and that brings this the reality view of how the imagination of text prompt into an image. This is exactly how this Stable Diffusion, which is primarily a generative AI image application, brings that imagination into the reality. I want to take a little deeper into some of the Stable Diffusion model. So as I mentioned, it's an open source Stable Diffusion model. Basically, which runs on the PyTorch framework as well as the Hugging Face open source frameworks. Hugging Face is basically a website which keep maintaining all the LLMs available in most of the different companies, as well as they are maintaining that different models for different LLM requirements. This has a key three components. First one is this CLIP, which is contrastive language image training. Basically this is the OpenAI model which used to convert your prompt into a vector embedding, which does the similarity search from the intelligence of this model and try to find the vector which matches the text prompt what the user had given for converting an image or generating an image. Then we have a unit, which is basically a denoising process. It's a convolutional neural network. What it does was it tried to remove the noise from the image and try to add the exactly what user has requested in the prompt into an image. And which has a variational autoencoder. Basically it does that encoding and decoding of the image to make that image into more highly resolution image at the end. I want to talk a little more about the latent diffusion model, one of the key architecture behind this entire stable diffusion. So which has 3 layers or 3 phases. So first one is the pixel space, then the latent space, and the conditioning space. The pixel space is basically an image will be converted into a pixels, and which has an inbuilt encoder that compresses the image into a smaller image, so that this smaller image will be given into the CPU for the better processing. Then this compressed image will be go into the diffusion process. Basically the diffusion process is all about adding a known noise into an image so that that noise will be removed later. So this diffusion process is all about adding noise and bringing that image into a pure noise. At the end of this diffusion process, this image will be given back into denoising process. That exactly where the noise will be removed by layer with the help of unit modeling, and every time it removes the noise, it tries to add an attention to the image. Basically the attention is like, it's a self attention and a cross attention. For example, somebody requesting a model to landing an aeroplane into the rainy day. So the aeroplane with the same body color, same wings, with a realistic one, which are built by the intelligence of the self-attention. But in the rainy evening or some sunset evening, if somebody requested for the prompt, that attention will be added as a cross attention, which comes from the conditioning. That will be given into the image, and layer by layer at the end, you could be able to see the image, what exactly the user has requested in the prompt. Then once again we have a conditioning module, which is basically based on the user input, which generates some of this semantic map. For example, if somebody requests a plane with a red color, so you try to get that attention from the user and try to feed that during the process of denoising. Similarly, any representational images, those all information will be fed during the denoising process. At the end, the user will get the compressed image. That will be again feedback into the pixel space, which is, what it does was it does decompress that image into the highly resolution image. Finally, that image will be given to the user so that he can able to see exactly what he has requested in the prompt. This is a typical architecture, basically how diffusion works and how image, a text to prompt will be converted into the image what the user has been asked for. Let me take a little deeper into some of the storage components of stable diffusion. So there are 4 key components which plays a crucial role in the stable diffusion. First one is the pre-trained model, which actually we get it from the Hugging Face network or the Hugging Face website. So where the pre-trained model we get it, which can be used for generating the images. Now the intermediate latent data, as I described the previous slide, every layer by layer processing happens. This compute, if it running out of any resources, it pushes back the data into the storage and try to read it back based on that the availability of the compute resources. So this temporary noise image also will be stored in the basically on the storage. Then we have output image, which is basically the user what they have requested in the prompt will be created as an output image and will be stored in the basically the data store, and this whole process will be recorded as a prompt. The prompt and the log information will be recorded in the storage. These are the key 4 components exist when you look at as a stable diffusion as an application. Now let me take a little deep into some of the key storage intensive components. So the first one is the model load, and second one is the generating images. So these again plays a crucial role in the stable diffusion process or the stable diffusion model. The model load is nothing but whenever the user wants to load a model, in a given point in time, the model will be loaded into the compute in a short time. And people, user given a choice to select the model based on their requirement. There are multiple models available which starts from 2 GB to up to 20 GB. The latest model which came from the Stable Diffusion is 3.5 large, which is almost 20 GB in size, which has been trained with 8.1 billion parameters, which has high resolution capabilities into the image generation. Again, this all options will be given to the user based on their requirement. He can choose to load the model and try to generate the image accordingly. So this is again very read sensitive operation. In a fraction of a second, he wanted to load the model into the compute from the storage and try to generate the image what exactly he or she wanted. The next one is the generated images. So at the end of this process of Stable Diffusion, the prompt would be converted or generated into the realistic image, which is actually write heavy, and closely 5 to 50 MB per image would be stored in the storage. And moreover, this image size also growing as and when the resolution of the images also grows. So as of now, we can see image is somewhere around 50 MB per image, but eventually it will grow as and when the resolution of the model also getting increases. The goal of this the paper is to talk about this on-prem deployment of the Stable Diffusion, and wanted to talk about the scalable storage provisioning for the Stable Diffusion application, and the way to stress this Stable Diffusion so that it really stresses out to the application and try to generate more and more images and stressing the both compute as well as storage. And I want to talk about some of the analysis what we have observed during our this exploration, and we wanted to highlight some of the key techniques or storage features to increase the lifespan of the storage devices. So let me start with the on-prem deployment versus the cloud Stable Diffusion deployment. So when you look at this Stable Diffusion or the generative AI image generation, lot of cloud providers are existed today, but the key thing is that on-prem deployments are evolving in the businesses. The key reason is the privacy. The business like marketing, the fashion technology is very sensitive to the innovation or the prompt what they have used, which is very sensitive because that exactly add the business value to their overall their business. Actually, that's exactly what the business delivers. So they have little reluctant to start using the cloud because of the prompt matters. The word what they have used, that prompt it really matters, and the image also will be stored in some public domain, which eventually impacts their business for long run. So they are slowly adapting and moving into more and more on-prem deployment of the Stable Diffusion or the generative AI technologies. Again, the next one is the control and the customization. See, if you look at today, that all Gen AI, what we use is all driven by what cloud provides today. If you want to build my own pre-trained data set, or you want to train that existing model with my own context or business context, or let's take I'm a fashion designing company. I wanted to build a model with respect to more fashion designing context, which is impossible in the public domain or the cloud model. Whereas in the on-prem model, which had given an option to train my model into more context aware or the business aware, so that I can generate more unique outcome based on what the user wants. The next thing is the cost effective. The cloud definitely give that immediate ROI because of there is no capex involved there. But moreover, in the long term, this on-prem deployment would help the businesses like some of the key businesses what I mentioned, like the marketing and the fashion designing. And the access, the clouds are limited with the API rates, whereas in on-prem we have an unlimited access. Since it's an innovative domain, people had an option to openly access as many tries to build their own set of outcomes. So with that, on-prem is going to be deployed in future, a lot of Stable Diffusion deployments. Now let me talk about how we can deploy the Stable Diffusion service. So it's a very simple, we need to install some of the tools with respect to the Stable Diffusion. Basically, this is a PyTorch based application. So we need a Python as well as a couple of Git and Docker libraries, and we need to have a GPU drivers. Then we need to clone the pre-trained model from the huggingface.com. Basically, this is the site where you can get the Stable Diffusion model, pre-trained models. Then we need to build an inference environment, how a user will going to access it and try to consume this whole Stable Diffusion infrastructure. That we can get it from the UI which is mentioned in this Docker based UI. The key thing is the provisioning storage for the model and the images. Basically, this whole application requires the provisioning of storage where we can store all our models, and we can even store more image. The images will be generated, will be stored in the exact storage what we provision into the deployment. And with the help of that, we can able to generate that image from the prompts. Now let me talk about what exactly the setup we have used for our deployment. So we built a disaggregated storage setup with the help of NVMe over Fabric over TCP. We have used SPDK 25.05, which is a recent release from SPDK. So we built it on top of AMD Geneva storage server, which hosted 32 16 TB TLC drives with the 100 gig network, which is connected over the initiator, basically where the Stable Diffusion service is running, which gives, on the initiator we need to have H100 or any GPU which is a good enough GPU to make this service more effective. And that initiator service where we have that 100 gig, which is again connected with the 100 gig network. This configuration or this setup gives the flexibility of disaggregated my storage as well as the compute. So as and when the number of users increases, we can scale my compute nodes. Same way, if I want to, if my storage requirement increases or the more and more users are generating images, we can scale our target also accordingly. Our storage servers also such a way that we can meet both demands and we can even scale independently. So Stable Diffusion is actually using the storage for keeping the model, keeping the checkpoints and generating the images in the target. Here's the typical Stable Diffusion EI, Stable Diffusion graphical user interface. So you can see that in the top left corner where the users are given a choice to select the model. So again, they are given now the users don't wait for a long time to select the model, they just click that model, the 20 GB of model weights loaded into the GPU basically. And also this has a prompt, basically the text prompt where user can give what exactly he wanted to generate the prompt into an image, which supports up to 75 tokens. And the good thing about the Stable Diffusion UI is that it supports negative prompt, which means you want to exclude some of the prompt or information for the image generation. So for example, you are generating something and you wanted to say, I don't want the blue in color. Ultimately, the blue will not be added into in your image generation. Then we have a couple of configuration parameters with respect to the Stable Diffusion. Basically, we can select the sampling method, which what exactly the algorithm behind to generate your images. Then we can configure our height, width, which is exactly the resolution of the image, and the batch size, batch count talks about the number of images can be created in a given point in time. This is exactly what a GUI graphical user interface of the Stable Diffusion. Along with image, text to image, this Stable Diffusion supports image to image generation. Even we can do the checkpoint merger. We can merge multiple model to make another model with a more detailed information, and we can even train with our own data sets. So this Stable Diffusion provides all this possibility where the enterprise can deploy into in their premise. Now let me talk about one of the challenges we had seen and the containerization of the Stable Diffusion, how it helps. by look at this single stable diffusion is a serialized processing. What does that mean is, when I give the when the prompt is generating an image, if that operation is happening, if I try to add one more if I try to give one more input, the new input will be queued until unless the previous one will be done, which was a bottleneck for multiple user environment, because only one image will be created at any given point in time, because the subsequent inputs or the prompts will be queued. So to avoid this challenge, what we found was we containerized this entire stable diffusion application into the Dockerized image, so that as and when the new user get added, we can host or we can spawn a new Dockerized stable diffusion service where the user can access the separate access and they can able to generate that parallel image creation with the help of this Dockerized process. So this gives the flexibility to the user to scale independently as and when the number of user grows. And in the left hand side, you can see that the Docker is being running on the multiple Docker is hosted on our initiator. So we wanted to stress this entire stable diffusion in our infrastructure. So what we done was we wanted to create a realistic workload to this entire setup. So for that, what we have done was we created a prompt.source file. Basically, what it has is almost thousands of user prompts, what basically user uses to generate that image. And with the help of multi-threaded Python program and this REST API support, we pick the random input from this prompt and try to give into this application, which generates that parallel images, and we stress that 25 containers at the same time. And this exactly generates that as many, it stresses both compute as well as the storage at the same time. So this is the workload generator for the stable diffusion application. With that, we stress the whole system. Here's the NVMe-top output, which basically talks about how this GPU will be consumed. So you can see that almost GPU is 100% utilized, and this memory also closely 100% utilization. We reach that maximum utilization of GPU with the help of our workload generator file, and which stresses that literally into the compute, and which eventually generated more and more parallel images in the backend. Here you can see that those images got created, and with the help of 4 GB model, we created 1024 into 1024 HD quality images, and parallelly these images are created with the help of the workload generator script what we have created. So let me talk about the key storage characteristics of stable diffusion. We have developed a tool to analyze these storage characteristics of stable diffusion. This tool leverages the Linux kernel utilities such as BLK trace, BLK parse, and the BTT utilities. And there is a Plotly library, which is basically open source Python library to deploy a graph in a much more interactive way, so that we wanted to highlight that what exactly the storage IO characteristics to here. And this with the help of this graphical user interface graphs, we have find that some of the key observations from our different operations of the stable diffusion of workload. Let me take into the first thing, this model load for a single container. So as I said, the model will be loaded into the compute from the storage. So whenever a single container would be running, we'll try to, again, this is the graph. I just wanted to highlight about what exactly the graph means. The x-axis talks about the time, and the y-axis talks about the logical block address activity. So in a given point in time, what exactly which logical block address being consumed is highlighted here, and the blue colored dots shows that it's exactly the IO activity on the given point in time against that logical block address. So if you look at here on the bottom one, the blue patch shows exactly when a model load of a single container happens. I just wanted to expand what exactly it shows. So if you see that the the LBA access is gradually accessing over the time, which is predominantly a sequential workload. So whenever a single container model load happens, the LBA is being accessed over the time very gradually. We can see that subsequent LBA is being consumed or accessed by the storage. So this gives a better read ahead and prefetching to the storage, which actually gives that more good advantage for the performance. But the next we wanted to highlight one of the other dimension of what we have seen on the multi-container load. Even though the bottom the workload looks like a sequential, I just wanted to expand that little higher. If you see that in a given point in time, the LBA access will be jumped, which exactly the sequential pattern becomes the random slowly whenever the number of users are increasing. So that exactly what brings the multi-container load from sequential becomes random when more and more users are getting added. So that limits the effectiveness of the read and the prefetching that eventually impacts the performance of the overall storage subsystem. So this is the block distribution of the model load. So we have a 128K read, which is almost 65% of IO, and we have a 256 KB read, which is closely 33% of IO. Then we have a 4K write, which basically some of the meta writes happening during the model load operation. So this is again the graphs are generated by the application what we have built to demonstrate what exactly happens during the model load operation. So when the single user, the pattern was sequential. When the number of user increases, the number of threads increases, the sequential pattern becomes random. That stresses the storage to more random aware than sequential aware. Now I wanted to talk about one another operations of the stable diffusion, which is the key operation or key activity is image generation. Whenever the user requested a prompt, at the end the image would be created and that would be generated into the storage or will be saved in the storage. So I just wanted that this is a bottom rectangle what I have highlighted is something. If you look at that, whenever that image is getting created by a single thread, this operation is a sequential write. It happens on the LBA sequentially. But at the same time, when multiple containers being looked at it or multiple containers are started generating the image, the IO becomes random. That exactly what we found, that whenever the multiple user or multiple threads are getting accessed, even though the pattern or the IO is sequential, this multiple thread becomes your nature of your storage is more in random. This impacts definitely the storage performance, as multiple containers or multi-user is the key requirement for any AML application, because the storage is not meant for only one user or one application, which was maybe archival or backup. We can use that. We can think that sequential can be the right candidate, but when you look at the AML, the multiple user is the bare minimum requirement because this is being used by multiple threads. So since random IO is getting into the AA, it also implies some of the challenges into the table. So it reduces the performance because sequential has an advantages of prefetching, read ahead, and the batch writes, which eventually impacted by the random workload. As we know that the storage subsystem is hard to predict at what exactly the IO pattern. And also it eventually, since there are more randomness being involved or scattered IO is involved, which eventually makes your write amplification factor is higher. The NAND eventually writes more data than what host basically requested. Then the GC also will be kicked or triggered frequently because of this randomness plays a crucial role. The random IO leaves some of the partial invalid blocks that needs to be fixed or needs to be GC has to be triggered to copy the valid blocks into the table and releases or erases the invalid blocks at the end. So this would definitely or potentially impact the endurance and the lifespan of the storage devices. So we know that the randomness plays a crucial role. We just wanted to try our stable diffusion with the FDP. So this the left-hand table talks about, the graph talks about the access granularity of the image generation workload. We have 128K, 16K, 4K, 32K access block size granularity during the image generation. So what we found was this, we just wanted to try this workload on FDP enabled versus FDP disabled device. So that one thing what we have figured out, that's a 20% WAF reduction when we use the FDP enabled device, which significant. So we just used 4 placement handle to trigger this workload and see how this is happening, and the result we see the significant reduction of WAF. But the WAF brings, definitely the reduction of WAF brings more in the longevity of the device, the durability of the device, and the performance also eventually added value to the overall stable diffusion application. I want to share this is a summary of what we have done it. So on-prem deployment brings a lot of control and privacy into the deployment. The storage is critical for the better user experience. We have provisioned NVMe-oF storage with the disaggregated and the scalable way, so that as and when user increases and the storage requirement increases, we can scale our storage backend along with the number of users. The random I/O is inevitable, especially on the AI-based systems. Since more and more users plays a crucial role, the sequential also becomes a random. So we need to start thinking how to build 100 billion IOPS storage, as exactly what we all are talking since morning, or even the FMS also, there is a big discussion on how to build 100 million IOPS storage. And the FDP, as we see, is reducing the WAF, which eventually increase the longevity and durability of the storage. And multi-tier storage is the key for the stable diffusion application, whereas the high performance tier would be used for having a latest models and image generation, because which is very sensitive to the time. And at the same time, we need to think the low performance tier, where we need to keep the old models and the archived images, because people will give an option to choose even the old model also, because sometimes some models give more precise information when they use the old models. So with that, I wanted to conclude, and I wanted to acknowledge the SMRC, the Samsung Memory Research Center, for sharing the GPU setup for doing this research. And yeah, thank you. And yeah. Yeah, please.
So I noticed that you use the NVMe-oF, you use NVMe-TCP. I'm really surprised that you're using AI Stable Diffusion, and which for storage, I'm assuming the GPU will require an RDMA session. So NVMe-TCP, no RDMA, so your performance could be severely hindered by not using an RDMA storage protocol. Yeah. Any reason for not using NVMe-off?
Yeah, it's a good question. So we tried both. Yeah. Let me reiterate the question. So the question was, why don't we use that NVMe over RDMA than compared to the TCP for better performance, because RDMA always expose the good performance. So yeah, so it's a so we wanted to bring this deployment model for more generic, because RDMA requires a specific infrastructure, especially the controllers or the HPAs or the NIC cards, which more in RDMA. So we just wanted to leverage the existing infrastructure with the Ethernet. Of course, as you said, RDMA definitely adds a value, which we'll eventually do that experiment in upcoming time. Yeah.
Your pattern analysis. So I assume you had a file system sitting on top of your storage. Right?
Yes.
V64 in this case. So all the analysis you did is essentially what the file system fair to assume that?
Yes, you are right. So the question was this exactly. We use that XFS file system on top of our block devices. So yeah, so the file system uses this. It takes that I/O and put it into the drivers.
So it's possible that with a different file system you would see a different I/O pattern altogether. Right?
There is a chance.
Maybe that's relevant for the context.
Exactly. Yeah. We use XFS based file system. Yeah, for these experiments. Yep.
Why FDP reduced write time? How did you assign the reclaim unit handle to the write?
Yeah. So in our experiment, so the question was, how did you assign these reclaim handles to the workload basically? So we use 4 placement identifiers for our experiment, and that the I/O distribution what we use, right, for 128K, 16K, and 4K, 32K granularity, we use that the different streams to write it into the different placement handle. Yeah. So basically what we think was that the prominent I/O, what had happens here is that the 28K, 16K, and 4K, and 32K. So which we find that the 4 placement handles is a good choice for making this a special application like this one. So we use that the block size. Block size plays the crucial role, what we found was that the 4K I/O is even bringing more WAF, so we need to play around with the 4K block size.
So in one of the requests you said that multiple containers are making it random, but I would assume that it would be the same model, same data, it should cache, and all the GPUs or the containers should share the exact same copy. Why would it become random?
Yeah. So good question. The question was, since the caching can be leveraged, how this big I/O becomes random. So the GPU is again very specific to the resource. So when we have multiple users being used, it always flushes out that the current context into back to this storage. Especially when we use more and more I/O getting generated for the image generation, which always every user has its own choice of the model. It's not like everybody uses the same model. One user can use 1.5, another user can use their own checkpoint. So every model has its own set of requirement. So the caching can be limited, especially the resources what we have in the GPU. So we always cannot expect that always the caches going to happen. So that's exactly what we have observed. Okay, I think it's a good question. So what we found was that most of the model load happens on the GPU here. So even though the 1 TB RAM we had, that GPU only consumed and loaded all the model weights into the GPU. So GPU is very resource sensitive. Whenever the new request comes, it tries to flushes out the current latent, especially the diffusion process, and try to take the new request. As I said, this is a single serialized way. It always try to find flushing the current caches and try to take the new request. So primarily the GPU is heavily used for this whole process of stable diffusion. Yeah. Okay.
That's the same question I have. Maybe you simulated different files in the file?
So the prompts are everything is different. So we always uses the new context, new model load, and try to generate the image. So every time we load, we load the new checkpoint or new model and try to generate the image. So that we always wanted to simulate that it really loaded freshly and try to flushes the image generation also back into the storage. Yeah, so it's a single device. What we have used is, yeah. So we just created a BDOF from the device and we mapped into the initiator and try to build the XFS file system on top of it. Yeah. Exactly. So we just got the FIO trace and yeah, we just run it on same FDP, same device with FDP enabled and FDP disabled with the same duration, and we have run it for 8 hours, and that's exactly the interval WAF what we have calculated here. Exactly. The application is not ready yet to modify it, but what we found was with this given workload distribution, we can able to achieve that better WAF reduction for the on-prem deployments. XFS, yes. Thank you.